Okay, so the first is that the first paper presentation is by Chen Chao. So you can just show that for the TS implementations, for example, the open SSLs, the wolf SSLs, and when flooding traditional binaries, we just need to mutate the randomly mutated the input, and we are potentially to find the bugs and vulnerabilities. But for some binaries like the TLS implementations, it's more like a protocols. I assume all of you understand what TLS is, and if not, I think Chen Chao will introduce a little bit. And the
Yeah.
second one is going to introduce by Nima is talking about a big picture of how the malware, how the malware, how the malware is involved and what's the observation of the existing malwares. Okay, so Chen Chao, please start.
Okay. Okay. Hello, everyone. I'm Chen Chao, and today I'm going to present this paper for the protocol state fuzzing of the TLS implementations. So before I doing the presentation, sorry. So here's all the information. The first order is called Jordi Tupper. He's a research engineer from SIDN Labs. His research interest is future internet architectures and design and analysis of the real-world security protocols. The second order is Rico Paul. He's an associate professor in the Rennes universities. His research interest is social security and formal matters. Okay, so here's some background information of TLS. TLS is called transport layer security. Nowadays, widely used, for example, HTTPS. So actually, many issues have been identified by a lot of research work in this area. At the beginning from 1994, actually virus versions of TLS has been released. The first is called SSL 1.2, 1.0, 2.0, and 3.0. And in 1999, it's renamed to TLS 1.2, 1.1, and 1.2. So the latest version of TLS is 1.3 and is finally finalized by the 2018. So let me do, before I do the presentation of the paper, let me do some quick recap regarding TLS protocols. The main purpose of this protocol actually is establish a secure communication channel at handshake between the client and the server. So you can see that actually a sequence of messages will be sent out between client and server to exchange certain information. First, they're going to exchange a pre-master secret. And the pre-master secret include the random number from both client and the server. And after that,
the random number is supposed to be only from the client, right?
Sorry?
The random number is also called a nonce. It is supposed to be only generated by the client, not the server. I mean, for your first step.
I saw that actually both client and server need to do the.
Yeah. So, but I just see that you are talking about the first step. The first step, the random number is supposed to be generated by the client, and this random number is generated by client. And of course, the server will generate another random number, but it is from the server side.
Yeah. I'm not actually following the order. I just saying that they
Okay.
need to do the exchange, which means they do the bi-directional. So in the first phase, they're going to exchange a pre-master secret, which is okay, and then after they exchange this pre-master secret, actually an actual key for the encryption will be derived by the pre-master key. A pre-master key they actually exchanged. And after that, after the derive of the encryption key, a change ciphers message will be used to indicate that they will start using the encryption by the key that agree on. And finally, the finish message will be used to conclude the handshake phase. The hash value will be computed based on all the handshake message in the previous handshake and will attached in the finish message for the verification. So if the server and client can both decrypt the finish message by the key and find out the hash value is matched, and they will conclude the handshake phase. And after that, the application data will be exchanged using this secure channel they just established. Okay,
so that's the overall description of the TLS protocol, right?
Yeah, correct.
So I think Chen Chao presents a very detailed process or the sequence of how the step 1, step 2, step 3. So I think that will be good. But what we care more is about the rationale and why we need to do this. So every step is designed carefully to satisfy the certain goal, right? So in
Yeah.
this case, because Chen Chao, you are going to fuzz such a library. So I assume that you're supposed to not only follow the steps. If you only follow the steps, it's very hard to find the get a very high get another view. So if you want to attack something, you must be an expert. So
Yeah.
now I have a few questions for you, maybe for you to answer. So
Okay.
what is the purpose of using hash? So I start from what's the purpose of using hash?
What's the purpose of doing hash? The hash is ensure the integrity of the message.
Integrity is for
Like the
integrity. So
integrity of the message.
that means during the messages, how
Yeah.
do I make sure the message I receive has not been tampered by some man in the middle, something in the middle, right? So anyone can because when there's some communications between the client server, especially during the handshake stage,
Yeah.
during the handshake stage, the attackers can modify any messages in between. So the hash is going to make sure the integrity of the messages. Okay.
Yeah.
So
Yeah.
for the protocols, so usually I assume that all of us are familiar with the cybersecurity background. I think there's also some expert, Junyang also have expert to here. So this part usually called asynchronous, using some called
Synchronized key.
asymmetric using asymmetric encryption. And this part is called the symmetric encryption, right?
Yeah.
So might ask what's the difference? Why we need to build a handshake using asymmetric encryptions, and why after we build the handshake, why we using symmetric encryption?
Okay, so interesting question. So actually, I think the whole purpose of the handshake phase actually is try to align some agreement on certain key that they want to use. So
So
yeah,
why we need to align some agreement?
because previously, if you do not have any agreement on the encryption of the key, then it's impossible to establish a security communication channel. Then yeah,
Okay.
then actually the entire handshake is still kind of like key exchange. Yeah. Yeah.
So here, maybe I can ask a question. Yufan, so have you ever learned cybersecurity lessons in your universities before you come to Singapore?
What's salary? What protocol?
The protocol is called TRS protocol. The protocol is that, so we're now using HTTPS, right?
Yeah, because I learned by Chinese, so I don't know the English name.
All right. So I assume that you're using SSL. So have you learned what's the symmetric encryption and then the asymmetric encryption, the purpose of using this? And have you ever used RSA? RSA, have you ever heard about this?
No, actually,
Okay,
no.
okay. So,
Sorry.
so you didn't have the background of securities. I think Junyang have this an expert. So maybe let me go through the general idea here. So from the very beginning, so when we are having the communications, everything is communicated in plain text, right? So, but however, some very sensitive information, like a bank account, user password and username. So when they are transmitted through in plain text, as long as someone in the middle is sniffing these credential informations, and your important and sensitive information is just gone, right? So in this case, we have to encrypt our messages from the message sender, and the message receivers have to decrypt the messages, right? So that's a very basic idea. So if we want to achieve this, we have to use some concepts called a common secret. It's called common secret. So once we have the idea of common secret, for example, it's just more like a key. So common secret is more like a string of binaries. For example, 1, 0, 1, etc. 1. And if giving a messages, it will apply some very simple operation like XOR with such a common sequence. So the messages have been turned into encrypted messages. We no longer understand what it is. Of course, there has more complicated way to encrypt the messages. And when the encrypted messages arrive the servers, the servers will once the server has a common secret. Suppose the client and server share the common secret. The server using the similar technique because this common secret is shared by both the client and servers, and the server use this secret to decrypt the informations. And now the client and server has built a secure channel, right? And all what I described is a part of this part is called the record protocol, or it's just called application data. Now the challenge is that how can the client and the server can build a common secret, because in the network application or in the web applications, if I'm going to visit another server, this server is actually a stranger to me. So now the asymmetric approach or this protocol, the ultimate goal or the rationale is that even the client and server does not know each other before their communication. There must be a protocol to build a common secret between the client and server, so that after the handshake or after protocol, the client and server can establish a common secret which can be used for their mutual communication, or build a secure channel or encrypted channel between the client and server. And as a requirement for the key exchange is that even someone in the middle observe everything of the message communication between the client and server. For example, the client send a message as a hello, client hello, and the server send a message as a server hello back, and the message is sent back and forth. Even if an attacker observe all the information during the handshake, the attacker still cannot infer what the common secret is. That is the ultimate goal of the TLS protocol. The protocol is to make sure that the clients build the connections and exchange the messages with servers, build the common secret. But even if all the messages have been eavesdropped and listened, but the client servers will build the common knowledges. The client server will build the common knowledges, but the attackers cannot infer that common knowledge. So that is ultimate goal. Okay. And as for the details of the protocols, so their client hello, server hello, the certificate, they will ensure some properties here. Okay, I hope that I make it clear. Chen Chao, please go on. Here, is there any questions here?
For me?
Yeah, I asked the other people. If there are no questions, we can keep going on, because that is very basic knowledge of the cybersecurities. I just want I would just to recap so that the other one, even without the cybersecurities, can still keep going on.
Okay, how should I clean out the?
Yeah, I'm clean for you.
Okay, so since I mentioned just now, okay, the TLS protocol is kind of popular nowadays. So actually, there are a lot of research regarding on this. But according to the statement by the author of this paper, most of this kind of research has been focused on the design and maybe the concept of the TLS implementation. But in the real life, actually, many security problems was due to the mistake in the implementations instead of design, like the way they design the structure of the software. Okay, another issue is that most of existing tools was mainly focused on the fuzzing of individual message or the configurations instead of different sequence of message. As we mentioned before, you see actually the whole process is it's not really a single message. Actually, it's a sequence of different messages back and forth. So the purpose by the paper, actually they want to test the virus TLS implementations, which means the real software, by fuzzing the different sequence of message instead of using the single message or the issuance certificate. This one is the unique point of these papers. Okay, so but how are they going to do that? So they introduce the idea of state machine learning. It's not really machine learning, it's learning the state machine. So the machine learning, the two are actually separated. Okay, so how are they going to do this kind of learning on the implementation of TLS? So the idea is like this. So they extract out the state machine information from the protocol implementations by a software called LearnLib. So what they do is they use the active automate learning. So actually the LearnLib will do the query to the implementation of TLS. And actually they will draft out this kind of state machine diagram based on the response of this kind of implementations. So this one will help them to find out the logic flags by analyzing those state machine manually after they extract out the information of the state machine. So this one is actually an example of how does the abstract the state machine image.
That is a result of the abstraction.
Yeah.
So maybe you will mention this later. So
Yeah.
it is quite understandable that the transition between each two states are message type, like the client hello server hello certificate, etc.
Yeah.
And how they define a state.
How do you define the state?
Yeah. So what we observe is that from the client side, or from the attackers, or from our side, what we see is that a set of messages, or what we observe is a set of messages, and each message is considered a transition. But the problem is that how do we define a state? Because we are going to learn a state machine, right? And a state machine is a graph. Each node is a state, and each edge is a transition between two states.
Yeah.
So if they're building, then how can they construct the states?
Okay, I will mention later. Actually, the state actually is constructed by the refinement. Actually, they have
It's a more like iterative process to refine.
Yes. So they keep changing the sequence.
Yeah, I'm not interrupting you anymore. Please keep going on.
Okay. Okay. So where was I? So in order to do this kind of state machine learning, the first thing first, they want to use the LearnLib. They need to have a fixed input alphabet. The fixed input alphabet is all the possible input can pass to the implementation of TLS. So in this paper, actually they are using the TLS version 1.2. So they include all the regular TLS message during the handshake phase, as all these kind of client hello, server hello, all the message that they are using, and plus a hobby extensions. So actually this kind of infamous extension because it actually lead to the security issue called hobby. Actually, this one is after the handshake protocol. So during the application data exchange, they want to maintain the active of the secure channel. So they will be able to send out this kind of hobby message to tell the server that actually the channel is still active. Okay, so they're going to test the implementation as a black box. What they do is they will not only follow this sequence of the message, they will shuffle the sequence of message and keep sending the different sequence of message to the implementations. And every single time they change the sequence of message, they'll produce a hypothesis based on the response of a server. And then they're going to compare the response with the actual state machine for equivalent checking. If find out actually the new state was found, they were just adding the.
So here you're saying you're saying that they compare the response from the server. So which two sides are under comparison?
Sorry?
You are saying that you need to compare two response from the server.
Yeah.
So I'm asking, what response are under comparison? What two response are under comparison?
Interesting question. So actually, I think the way they do it is kind of so they have like a ideal type of state machine, and it's kind of like doing the fuzzing. If you find actually the new path you're adding onto the graph.
No. So here, so anyway, we are trying to fuzzing. Fuzzing means that we need to find the vulnerabilities. If we want to find the vulnerabilities, we definitely need to have a reference, right? We definitely have a reference, but given that the protocol is very complicated, you need to build a state machine. So I'm still trying to link the logical line between your story. So you are saying that giving that, so in this, in your slides, the ultimate goal is that how to build a state machine. Am I correct?
Yeah.
Yeah, it's about if it is a graph building techniques. So why do we need to compare the response? And then, and also you mentioned that how to mentioned that you need to check the equivalence of the actual state. So how do you define the equivalence? You just going to report. Do not need to flipping the papers. I know that you're just flipping the paper trying to have a reference, but you're supposed to be grasp the gist of the papers and represent it. So do you have any answer for my questions? If not, we can just go on. I try to infer some information from your slides myself.
Okay. Actually, so is how should I put this? So the understanding I have is kind of like this. So actually, they have a baseline of the reference, like the normal behavior of the input. And like I send out the client hello, the server should return me a client server hello. But there's some scenario that when we change the order of the sequence of message, actually when we send out the client hello, and the server actually didn't return the server hello, maybe he returned something else, like alert or error or unexpected behavior. And this one is not equivalent to the normal behavior of the ideal state machine. So this one, when they find this kind of behavior.
So here come questions. Where does this ideal state machine come from? So we need to manually verify, manually construct the ideal state machine, or we learn them because you mentioned. So I'm just quite confused. So here you say that we're using a state machine learning algorithms. So somehow when we observe the interaction between the client and servers, we are going to automatically construct a state machine, right? You also mentioned that there will be an idea state machine. And how do we construct such an idea state machine? So all we do this manually, or
this one is handled by the learn lib. Actually, it's mentioned in another paper. So
by who?
By who? I mean, reference.
By another paper. So here, let's kind of clear. So we're supposed to have an idea state machine. Am I correct?
It's not really ideal state machine. It's just like a set of behavior of if you are following the TLS protocols, so the expected response from.
Yeah, so I understand you can provide an input alphabet. There also including heartbeat. So when we're talking about fuzzing, we need to know. So let me make my question very short. So once there's some phenomena happens, or once we generate a random sequence of interactions, and how do we know that we found a bug?
How do we know we don't found a bug? Interesting. So as I mentioned, just like if you send the client hello, you should receive a server hello.
Yeah. So we somehow need to using such a definition in the TS library. So consider this. So for now, think about the very simple software testing scenarios. Suppose giving a calculator, we input 1 + 1, and the programs will output 2. right?
Yeah.
So that's a very, very, very simple examples. But however, if we go to another planet called Mars, and their calculus or their ideas, they are very different from our Earth. So how do we know that if my input is 1 + 1 and output be 2, somehow we need an assertion or a specifications. So in this world, there are actually no specifications, no exact specifications. There's always consistency. So when the output of the programs is inconsistent from our expected value, suppose
Yeah.
it's output 3 and we expect 2. So we know that this program have the bug. Am I right?
Yeah, correct.
That means that we always need to have a reference. We always need to have a reference to infer whether the given output program is we expect.
Yeah.
You're right. I'm right.
Correct.
So in this case, so let's come back to your questions. Now this one is the TRS library.
Yeah.
TRS library. And our input is not a 1 + 1 anymore. Our input is client hello. And
Yeah.
our input is the client key exchange messages. And anyway, the TRS library, so once it's deployed on the server, will give us a server response.
Yeah.
Right? So
Yeah.
how now comes questions. How do we know this response is correct? And how do we know that when we're giving you are saying that we treat the TRS implementation as black box. So we cannot see any exception happens inside the TRS library implementation, right? So we can only infer the informations from the server response.
Yeah.
And when their server response comes, and how do we know that it's just what we expected?
So I don't know. So as saying that the server actually we're going to return something to us, right?
Of course, yeah.
Yeah. So if we send out the client hello and they return, it's not client hello, maybe some error message saying that it's incorrect. So
and I assume that suppose we maliciously modify the client hellos, and it's quite normal for the server hello to respond something that we get out of expectations. For example, the server client hello saying that I do not know what it's saying. So how do we define correctness? So the idea, so we just answer the first question. How do we define the correctness? Only if we can define the correctness or have a good reference, then we can find the vulnerability and bug of the TS library implementations. Later on, there's another kind of questions like we are building state machines, and now there are so many messages, and how do we define the equivalence? So giving two messages, and we now they will arrive in the same state, and that is also another question. Okay, if you do not answer, let's pass this. Let's pass this, and you can go
no,
to the next slide.
It's interesting. So actually, I didn't quite get the question.
You didn't quite get questions. Anyone get my question?
So you are saying that how I know that actually there's something wrong with the server?
So that's a very I think I made myself understood. So the first question is how do I know? Because when fuzzing means that we're going to find some vulnerabilities of the TRS library. So in this case, we have to define, unless we define something, if we want to find something incorrect, we have to define what is something correct, right?
Yeah.
And so my question is that what is something correct in this paper or giving in your presentations? And the second question is that giving these state machine learnings, and you are saying that equivalence. So equivalence means that giving two messages, maybe the different messages. We know that these two messages will lead to the same state of the server. And how do we know this?
Oh, okay. Then I get your point. So you're not saying that how should we find the error? So you're saying that how should we find the error actually linked to the same state?
There are two separate questions. So can you address the questions? If not, we can keep going on. Maybe we have ideas in your next slide.
Yeah. Maybe we can discuss this offline. It's taking too much time. Yeah. Okay. So where was I? I just continue to do the freezer. Okay. So. Okay. So the state machine, after they extract out as a result, actually in the paper they actually test out 9 different implementation of the TLS libraries, and they actually test both client and server implementations. Actually, there are 3 main things they are looking for when they try to manually analyze extract the state machine. The first, they want to see whether there are more paths than expected that lead to successful data exchange. Normally, there should be only one path lead to a successful exchange application data. When they found actually that when you find actually there are more than one, they don't necessarily think that you're wrong, but maybe they require some further investigations. And number 2, they want to see whether they contain unnecessary state than the normal TLS design. So which means that maybe there's something wrong during the logic implementation in your codings. And number 3, they try to find any unexpected or interesting behavior that's not defined in the TLS protocol. But finally, there are 9 implementations were tested, and actually they find 3 new flaws was discovered in those 3 libraries. Actually, we are going to elaborate those flaws one by one. Okay. So the first one, after they get a state machine from the GNU TLS 3.38, actually there's some interesting finding. The first finding is actually there are 2 paths leading to a successful application data exchange. So actually, after the further investment, they found actually it's acceptable because the first one is a regular one. The second one is actually where the empty client certificate is sent. Since author saying that actually they didn't care about the client side authentication, so this one is acceptable. And then when they deeply look into the state machine, they find that actually the shadow path was found by sending the heartbeat response during the handshake phase. Actually, the heartbeat response should be sent during the application exchange. They find that actually during the fuzzings, after they're sending a handshake, after they're sending a heartbeat response, the server will return an alert message and then terminate the handshake phase. And they look into the source code. They found that actually for the hash computing, as I mentioned before, for the finish message, a buffer was used to collect all the handshake message. And then in the finish message, they will compute the hash for them. But these buffers will be reset upon receiving the heartbeat message. So the alert will be sent out due to the mismatched hash value. Then this one is an issue found by these kind of measures. And this bug could exploit by bypassing the integrity check based on the hashing. Okay, so this bug actually was reported and fixed in the GNU TLS 3.39. And after the bug was fixed, actually they do another state machine extractions on both version 3.8 and 3.12. Okay, actually you can see the right side one is actually much more simple than the left side one. So the extra path was actually removed. So they confirmed that the bug was fixed.
You need to interrupt a little bit. So in this case, so the green line, so the here's you haven't introduced how the state machine is constructed.
Yeah.
So based on what I described present, it seems that we have a referenced state machine, and somehow we observe the implementation. We observe the implementations of the TLS and to observe whether there's additional and the missing messages happens in the state machine. Yeah. So here comes questions. Where did this reference state machine come from?
Where does this reference state machine come from is, the paper actually is based on the normal behavior of the TLS library. So it's not library, it's TLS, the definition should be come from like this.
Okay, so let me interpret. You can see whether I'm correct or not. So overall, if we want to test whether TIER's library has the correct implementations, now in this paper overall, consider the TIER's an arbitrary TIER's library implementation as a black box.
Yeah.
And we somehow need to mapping its behavior or we need to map its runtime behavior to some specification. The specification or the assertion is something like we input 1 + 1 and it's supposed to respond 2.
Yeah.
Using the TIER's library, it is very complicated protocol. So overall, a protocol can be generally described into a state machine. So the state machine was showing that now I'm now in the state of the from the very beginnings, I'm going to send a client hellos. So now I'm in a state of what? So when the server got send the message of the client hello, the server will be actually turn itself into a new state and send another messages. So by this means, there will be supposed to be a standard state machine constructed based on the TLS 1.2 protocol.
Yeah.
And when we have such a protocols, we're going to randomly generate the message sequence between the client server of the real implementation and to see whether the messages whether the exchange messages will introduce some additional transitions or introduce an additional state, additional state described in the reference state. So the reference state is is manually constructed, or it's considered as a priori the priori information in the paper. It assumes that such a model has been exist will serve as an input of our approach, of their approach.
Oh, okay.
Am I correct?
Yes, yes. So they have like so actually they didn't mention in the paper, but they just do how they just saying that they check for equivalent.
Well, here I just observed that I'm not sure how much time you spent on reading the paper. There are some very important questions you haven't been addressed. So that leads to the confusions and the puzzle. These confusions and the puzzles are in your discussions. If you can well prepared it or spend more time, or if you have problems, you can discuss with me. I think you will save a lot of time during the presentations. And all what I do is to clarify what it is exactly doing, and what do we need to infer. For now, we do not present just for being present. We do not present for presenting. We try to present existing work to see whether we can borrow some ideas to have another publication. So that is ultimate goal. So you keep going on. So let me think.
Okay. 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 So there's another issue was addressed by the paper saying that actually they find another issue in the Java secure socket extensions 1.80 and 5. They also find actually the several paths leading to a successful application data exchange. But the interesting thing is that actually they find out as long as the no finished message was sent out, a duplicate message are acceptable by the server. For example, the subsequent client hello and client key exchange are also accepted by the server as well, even you send out this client hello and client key exchange before. So this issue was exploitable and will trigger the server to accepting the plain text data. So after you send the subsequent client hello and client exchange, you find out actually the change cipher suit from the client will be omitted by the server. But the server will still respond a change cipher suit to the plain text finished message by the client. In this issue, the server will still send the data encrypted, but expect the data unencrypted for the client. This part.
Sorry, so I think we need to skip those examples. When we talk about these examples, I think we need a more detail and context to fully understand the vulnerabilities. Maybe you pass the examples, and I have a question to ask you. Maybe you can pass these slides.
Okay, actually, this is the last few slides I have. Actually, this paper is yeah. So yeah. So for conclusion, actually, it's an effective method to reveal the logic flaws in the TLS implementation. And
feel that these presentations do not have the so may I ask how much time you spend on reading the paper?
actually, I spending the reading the paper to 2 entire days. Yeah.
2 entire day.
Yeah.
So, what do you feel? Do you think how much do you think how much knowledge do you think have you grasped the idea of this paper?
I will say that's at least 80%.
At least 80%.
Yeah.
But if it is 80%, why you cannot answer the question as and where these reference state machines come from, and also how do they consider the equivalence? And they are all very important messages or very important points in the paper that they're missing.
Yeah. So to be honest, actually, that I do spend some quite of time to read a paper, but actually the most half of the paper is talking about those examples. Actually, the state machine learning dimension actually only like half page. So I just present whatever he said in the paper. Yeah.
This is supposed to be a top tier conference paper, right?
But for state machine learning, actually, they just say that actually they send off the equivalent and all these hypotheses. Yeah.
Now this is the implementation level fuzzing. So if we can borrow their ideas, we can somehow have can save the fuzzing efficiency, because from our side, we still need to generate a sequence of messages to see the implementation issues. Of course, if we want to test it, we somehow supposed to be an expert in Tier's protocol. Otherwise, if we just tested it, we tested it in blind way. So we will not be very efficient to compromise the protocol implementations. So let's talk more about these things in our next Monday. But before we meet in next Monday, so I hope that you can come up with answer to 2 questions. All about both about this paper. The first question is that where is this? You would like to make sure construct where the referenced state machines come from. So it's more like a consistency or the matching problems. So we still have a reference, and if I understand correctly, it's going to check the messages sent and received between the client and server to see whether the giving messages conform to the specification. And the second is that more from the technical levels, when we have such a messages observed, and how do we know the messages conform to the specification? So that's more about the technical details. It's very easy. It's quite trivial to know that these messages is kind hello, but the difficult or challenging part is that how do we know when I get this kind of client hello, or when I get 2 different client hello, whether these 2 client hello leads to the same state? That is a very, very key questions in this paper. Okay, I think that's all my comments. I suggest that you may go through the details, and maybe when you go through details, maybe you still need to equip yourself with some TLS protocol knowledges. Yeah, so to see what is the DHE key exchange, and what is the potential, and what is the most popular cipher suits, and in the cipher suits, what is the encrypted, what is the most popular encryption algorithm we used, and the idea of the public key and the private key. I assume that you have this knowledge, right? So the public key, private keys, and also there's if and how they are, why they are designing in such a way, and what is a potential threat or what is potential cyber attack they're going to prevent. We need to equip it with you need to equip yourself with all those kind of knowledges in a very clear way.
Okay. Thank you so much. I will.
Okay, thanks, Chen Chao. So in next Mondays, you just further investigate 2 questions. Let me repeat. The first is that where is the reference model come from? The second is that when we observe the messages communicated between the client and servers, and how do we now choose data equivalent?
Sure.
Okay, thanks, Chen Chao. So the next one is supposed to be Nima.
Yes. Let me share my screen. Okay. Hi everyone. Today I will present you the following paper, a lustrum of malware network communication, evolution, and insights. So the paper is quite interesting as it provides a very comprehensive study of the domains used by malware and PUP. PUP means potentially unwanted programs. So they can be softwares installed secretly with an installer, like So a quick look at the researchers. Basically, they are all in the cybersecurity field, and they all have an interest in the network security field also. Okay, so this is the agenda. And first, let's go to the motivation. The researchers have written this paper because even though network information are used for threat detection, the efficiency of network detection signals derived from dynamic analysis was never studied before. So this paper fills the gap by doing this study. And moreover, they are doing it on a huge data set. So we will see how the dataset was built because it's one of their core contribution. Ultimately, the goal of the paper is to provide a view of the network infrastructure, the malwares used in a 5 years time period. So this is the time period. Yeah. So let's go to the datasets. So this is the structure of the datasets. The researchers use multiple sources of data to construct it. So first of all, they collected a malware execution dataset of 26 million unique samples. So this is this block.
Million unique samples. Does these samples all come from the virus total?
No, they come from 3 sources. I think
they published, but there is a work maybe 4 to 5 years ago.
Yeah, it is very old, but it is not published anyway. Like
it's not published. Okay, so I just book the malware from virus total, but I find it is super big. So I'm still thinking about how to pass these. How to pass the malware? Maybe 100 gigabytes. A few hundred gigabytes. So
okay, if you maybe we can meet. I have a hard drive that could.
Yeah. Okay. So we do have a hard drive, 1T hard drive, but our hard drive is quite occupied in these days.
I have one. It is not a problem, I think.
Okay. Okay. So let's discuss more about how to collect this data later.
Okay. So their execution dataset, malware execution dataset is the union of 3 datasets So one come from their university, one come from an antivirus vendor. They didn't mention the name. And the last one is called the NUS dataset, but the website associated with it is offline. So yeah.
So no worry. So anyway, in this paper,
It's very old.
They executed every malware or every unique malware samples.
Yeah, they executed every sample for 5 minutes. They said no longer than 5 minutes.
Sorry.
They executed each unique sample for no longer than 5 minutes.
No longer the 5 minutes. Okay.
Yeah.
Okay.
Yep. So yeah, one thing to be noted is that it's really huge, like 26 million. They said that it's
It's a huge number. It's a huge, impressive number.
Yeah, compared to the other papers that were published at the same time, yeah, it's very huge. And okay, so to add some information to this data set, they used first virus total. So by passing the MD5 hash of the samples to virus total, they were able to get like their first apparent state and the detection level. Yep. Yep.
It means that about 3 million of the samples, because they have the 20.
3 millions. Yeah, they didn't have
20.8 or 220. Oh, okay, that's 26.8.
Yeah, 26.
So that means 3 million. About 3 millions of the samples is the first appeared. First time seen by the virus total.
Yeah.
Okay.
Okay. And then there is an interesting part with the domains, like because in their execution, they
will record the domain names,
exactly,
IP addresses, communicated within these 5 minutes.
And
what is the result?
They wanted to like classify these domains to see if they were benign or if it were noise, but we'll talk about that later. But they used 5 sources to do that. And the most interesting one is this block DNS records. Is everyone like okay with DNS, the concept of DNS?
Sorry?
Is everyone like okay with the concept of DNS, or do I have to explain it?
I think DNS is quite a common knowledge by all of them. So, all of us.
Okay, so basically, these DNS records came from American ISP. So the researchers were able to get this record with a 5 billion size from ISP that was kept secret, and the data were anonymized. So that's a really like difficult to obtain data.
So how many IP have they collected?
Sorry, can you repeat?
How many IP addresses?
The
IP is there's a 5.2 billion IP address.
Yeah, like domain and IP pairs.
But the same domain, different domain may lead to the same IP.
Different domains.
Yeah, sometimes may lead to the same IP.
There are also the contrary, like they may be like dynamic DNS, and they may lead to different domains to the same IP. Yeah, exactly.
So let me interpret your graph. So here, by the way, so may I further specify the DGA? The DGA.
Yeah, let me maybe explain all the it's not very long. DGA archive is is a website that exhibits domains that can be generated by domain generation algorithms. We have talked about that in one of meeting. It's like when a malware is generating the domain.
You mean the malware can regenerate a new domains?
No, basically, an example is that to not hard code the domain into the malware, we can like set it to connect to generate a domain with an algorithm. So a simple example is that you take the dates, you concatenate it, and this is your domain.
Yeah, but we have, but the domain name can be anything, right?
Yeah, it can be anything. It's just an example.
So what's the difference between the domains in the DG archive and not in the DG archive?
DGA archives is just like known domain from DGA malwares.
Okay, so it's more like, but how it is different? Okay, so
it is
can I consider it as a special kind of a blacklist?
Yeah, exactly. Yeah.
Okay, we can run these 26.8 millions, and I think almost half of them, more than half of them are their domains have been listed in the DG archive, and 8 million is from Alexa. So that means that means the malware were connected to some legitimate or some famous the big.
We will come to that like in the next slide.
Okay,
but
also there's a small portion of them that's in the public blacklist. And
I think that this public blacklist is a concatenation of 8 datasets, if I remember correctly.
Yeah, and also a lot of them are not alive. They have been expired.
Yep.
Okay.
And they also take the expired domains. We'll see later.
Half of them are expired. More than half of them are expired. Okay, please go on.
So now the next step is to actually use the dataset, but before, one of the core contribution of the paper is the filtering process. So you may ask why we need to filter the data. It's because when the domains were recorded in the malware execution dataset, there are naturally some noise. So first, the noise is because of benign apps like Windows itself, when it's making requests to, for example, updating. So this is the first icon. But there is also noise because the malware can make requests to benign domains. They do not interact with exclusively malicious infrastructures.
But what's the point of the malware connected from the big IP? Maybe okay. Google is the some gets used for to check some things. And what is the most popular Alexa domain in the malware?
It is considered like benign.
Yeah, I'm asking, so what we are discussing is that malware may visit some legitimate and benign domain.
Yeah.
Right? And
right.
My question is, what kind of legitimate and benign domains are the most popular among the malware? Have the paper mentioned this?
No, the paper is focusing on the malicious domains. Okay. Because it wants to analyze the infrastructures and interactions between the malicious domains and the malware.
Okay.
So let's go to the filtering process. It's done in 4 steps. It's not very complicated. First, invalid domains are removed, like domains that were not resolved by DNS. They mentioned that requests to non-existent domains are primarily due to domain generation algorithms. So it's a mean to mitigate the impact of these on the study. The next step is to delete like a benign domain from the Alexa. Next step is to delete what is called MX lookups. So these MX lookups correspond to DNS requests that are used to find mail servers of a domain. The number of these domains can be huge because it is linked to mail spam behavior of malwares. And the paper mentioned that it is the study of spam is out of scope. So they removed all these MX lookups. Then they deleted reverse DNS requests pointing to large ISPs and hosting providers. They explained that these requests correspond to, for example, Windows behavior when using the logging. So they removed it. And
Okay.
when they execute these 4 steps, 20 million malwares remained. So out of the 26 million, like the other one, it means that the other one were not. There were no domain. Like yeah.
Okay, please go on.
Okay, so note that we have a filtered data set. The researcher studied properties about the collected domains. One of the points is that you may ask why the researchers are interested in domains and not just on IPs. And they justify that by saying that malware communication often relies on DNS and domains. Yeah. Okay, so let's look at their results. Maybe I should. Do you see the graphs?
Yes, I see.
Okay, perfect. So this is the first analysis. So on the red figure, you have the number of what is called the E2 LDS. You can take it as domains. Yeah, it's effective. It's the effective tool level, but you can take it as a domain, and you have the number of MD5, so the number of unique malwares in the x-axis, and you have the number of domains that were associated with these malwares. So this red figure shows that most MD5s resolve less than 10 unique domains. So a more interesting thing.
That the malware always changing their new domain.
Yeah, exactly, exactly, and most of and on the blue graph, we can see the number of day a domain was seen, and we can see a peak at 1.
Yeah,
and,
very similar to the phishing, right? Very similar to the phishing website. So, given the phishing website, it only lasts for a few days.
Yeah, so let me. Maybe it's better like this.
Yeah, I think that's fine. Let's keep going on.
Okay. So here the interesting results. This is an interesting result because it suggests that most domains are used like only once by a single malware sample in the dataset. And this leads to the interesting fact that blacklisting malware domains observed during dynamic analysis does very little to prevent future communication from newly discovered malware sample. So that's a intuitive result, I think. Let's switch to the second results. The second analysis is about dynamic DNS. So dynamic DNS allows the server to update its record. So it's very simple. And this figure reports top 100 of these dynamic DNS that were observed. And also, they sorted it by the number of malware samples curing them. So
I'm thinking about giving the malware. I think IP address is enough. Why the malware have to use the domain? So if I'm doing something malicious, of course, if it is a phishing website, of course I need a name for that. Maybe the tricky names can improve my chance to compromise the victim. But if it is a malware, I think IP address is just enough, right? IP address is just enough. Why we need to have domain? Well, maybe it's okay. I just it's just.
Let me think about it. Maybe I have the answer at the end.
And also we have based on our malware analysis technique. For example, the trickbot, we just have a list of IP address, right?
Yeah, for trickbot we only have a list. That's why when the researchers said that malware communication was based on DNS rather than static IPs, I was
You're curious because it's not what we observe.
Yeah, but I was saying myself that maybe it's only trickbots, like maybe the others are different.
So I'm not sure. Maybe
maybe it's old. The paper is old, so maybe that's the cause.
Yeah, I just feel that it's not necessary to additionally because the malware it's not like 20 years ago. The hackers just hack the victims for fun. Nowadays, the hackers to apply their attacks for money. There's in the darknet there is a very mature economic and commercialized chain to sell the malware, construct the malware. Sometimes you propose your requirement and specifications, and their specific provider to automatically generate a malware for you to connect attack. So in this case, why giving we have some economical considerations. Why bother to have a domain? IP address is just enough. I just raised these questions. If someone else will continue, if not else, we can just have a discussion.
Yeah. Okay.
Okay.
So back to dynamic DNS. Their conclusion was that they were commonly used across many malware samples, and they said that it was because they took the example of the first one, the one that was the most cured, and they said it was free, so it's a free service, and it also offers unlimited registrations and an API for account management. So they said that it was very attractive for malware authors.
I'm sorry, very attractive for what?
Malware creators.
The malware creators.
Those who created the malwares.
Okay, keep going on.
Okay. In a similar way, they did analysis of all the CDNs that were involved. So CDN are frequently used to to serve contents from geographically distributed data centers to provide performance and availability. So for example, when you are on YouTube, if the YouTube servers were only in America, it would be very slow, but they are distributed around the world, and the requests go to the closest.
Sure.
So that's the concept of CDN, and this figure includes some of the larger CDN, and what the researcher said is that it allows the malware traffic to be similar to benign traffic.
It depends on how they define the similarity.
Exact. Yeah, but yeah.
Okay, please go on. By what?
Okay, that's a very interesting one. It's on passive DNS and blacklists. So this figure describes the time difference between when the domain was first seen in a passive DNS or public blacklist, so public blacklist and passive DNS, and when it was first seen in dynamic analysis. Let me.
So how they define the dynamic analysis? Does that mean they interact with the malwares, or they?
It's their data set, like the data of execution.
But after executing, what do they record?
So could you repeat?
So when they run the malwares, what information they record?
Data of execution, the MD5, and the domain names.
So they only collect. So they only the traffic. Didn't they collect the traffic? Hello?
Could you repeat, please?
So I'm asking the question. So when we run the malwares, the authors collected the domain names generated by the malwares and the data executions. And
yes.
what else? I assume that they still record the traffic, right?
The recorded traffic is not included in the data sets.
Okay, so but
they just record the domain names.
Okay, so let's go back to when they run the malwares and what kind of dynamic analysis result they have. Okay, let me keep introducing.
This axis is like the number of domains that they count in their data sets, and this axis is the differential in days.
The differentials in the days.
So if we are on the left, it means that we are before the malware discovery. And after 0, we are when the malware was discovered. So, for example, let me interpret this, the A with the blacklist. So we can see that the majority of domains count, if we add them, is after 0. It's they give the number is it's 70% of them that are after 0.
After 0 means that 70% of them.
That means that they were added to public blacklists after we have seen them in dynamic analysis. So this means that this only means that the delay that we can have between first appearance and blacklisting could be reduced by relying on malware analysis to populate domain blacklists.
So here, what I've seen is that sometimes when we run a malware, its domain has already been in the blacklist.
Exactly.
However, when we run a malware for certain times, if the domain is not in the blacklist, we are going to estimate how long did it take to be put into the blacklist.
Correct.
And the color means so pub. What does the PUP pub mean?
PUP is it's what I said in the beginning, is like potentially unwanted program. Yes. So it's, for example, it's a spam software, not spam software, but you know, when you install a software in the setup process, you have a box that are already checked that download malwares by default.
Okay, so sometimes like the unwanted, more like unwanted programs and the malware.
Yeah. And I didn't say how they come up with this classification because for me it was a detail, but basically it's by taking the various total metadata with the AV detection label.
Okay, no problem.
And what they call unclassified, it's when the AV were not detecting it.
Okay, okay, so it's not confirmed by the virus total.
Yep, but yeah.
And what's the difference between the PBL and the passive DNS?
Yeah, PBL is passive blacklists. So let me interpret maybe the passive DNS for you. So passive DNS, remember, it's the dataset they collected through the American ISP. So basically, a lot of people in America like have their DNS set to the ISP DNS. So the ISP were able to record the DNS requests. And what we see here is that after the malware was discovered, the number of the count of domains is significantly reduced. So it shows that it is efficient to block domains based on malware analysis. The two figures are linked.
There's a lot of reasons for that. So the first is that the first graph told us that it take a longer time. So it takes maybe a few hundred days to put a malware into a blacklist. If we just look at the blue.
Okay.
So the blue part, is there an overlapping? Will that be an overlapping? There's no overlap. There's no.
I don't think it's overlapping.
Yeah, I don't think so too. So it seems that a lot of malware, suppose we just look into the green ones. I think quite a few malwares. It takes quite a while for many malwares to be put into the blacklist.
Yes.
Right. And
but also the majority of them are added after they were discovered by dynamic analysis.
Yeah. So
and here we see like the reduction of the reduction of the requests.
So once a malware has been found, it will appear, its domain appear less in the passive DNS.
Yep, correct.
But however, it still take quite a long time to be put into the blacklist.
Yes.
Don't you think this conclusion is a bit contradictory?
It might be, but I think that it might not be also because these are public blacklists, and this passive DNS also reflects like the usage of antivirus, and maybe antivirus have their own database that are not public.
Yeah, I agree. So yeah, I mean also that once the virus disappears, the antivirus companies may have a way to classify it. But it may not, because sometimes blacklisting is one way to prevent the malware. We are supposed to have multiple way to recognize the malwares, maybe using machine learning based approach. In this case, there's not necessary to put the malware into a blacklist.
It's not the malware that is on the blacklist, it's like the domain, but yeah.
Okay, it's a domain, okay. Okay, keep going on.
Okay. Okay. This one is very interesting. It's on domain lifetime. This figure shows the density distribution between the number of days a domain was resolved. So it's the y-axis, and the lifetime of the domain in days. So that's the x-axis. Let me take the malware, the green one.
Right. So the idea is that the lifetime in days, the number of days resolved.
So let me take, because we see there are 3 hotspots like here, here, and here. So in the bottom left, we can see if we interpret these black spots, these hotspots, there are a large number of domains that are short-lived, so they have a very low lifetime, and that are rarely resolved. So they were not resolved like this one.
The point is that what's the difference? I'm asking what's the difference? What's the difference between a malware if he is not alive and if he is not resolvable? He is not resolved. Resolved means that.
Okay. I see your question. I think I'm answering it. How did they get this lifetime? Maybe that could answer.
They visit the domain to get a response. I assume that is the case.
Yep.
And the result means that the DNS can still resolve the domains into the IP address, but this IP is not alive anymore. Yeah, I think it's supposed to be correct because there's the diagonals. It will be there the diagonals here, right? There's not supposed to be any data points here, so it means that the lifetime will always be longer than the resolved. May not necessary.
Yeah. Okay. Okay, I understand.
It means that if cannot be resolved, but it is still alive for a long time.
It means that the domain is alive, but there are no malwares like contacting it.
Sorry. So here, suppose giving a point here, it means that it is still alive. It is alive, but it's not resolvable. It is unresolved.
It is resolvable, but in the data sets, there are a few malwares that actually resolve it.
The number of days. It's the period, right? The number of days. What? Still somehow. So, what we're talking about is a malware domain, right?
Yeah, malware domain.
A malware domain. And can you give us a definition that in what case in what case a malware domain is not resolvable?
You mean it's not that it's not resolvable. It's that
It was writing. It is written there that the number of days resolved.
resolved. Yes.
Yeah, what do you
But
mean by resolved?
by resolved, I mean like the number of days that a malware that in their data sets a malware was contacting this domain.
The malware is contacting this domain.
Because they can be a domain that is always alive, but no one is contacting because I don't know, like maybe it's we can imagine for TrickBot we have seen that there are modules. Maybe there is modules that are really expensive, so people don't buy it, and the domain associated with.
So let me ask a question. Maybe I'm ask questions. How long will a domain name? Because when we're talking about the malware, when talking about the malwares, we're always saying that. Oh, wait a minute. It's quite a heavy rain out there. So I'm saying that, so I'm trying to draw conclusions. We know that for the phishing email or the phishing URLs, the lifespan of phishing URL is very short, only a few days. But what is the lifespan of the malware? And how does this how does this diagonal lines mean?
Okay, I think that you point a very interesting point. The diagonal line is important. Like let's compare it to the PUP. We can see that the density is along the diagonal. So first we might ask why it is not all the diagonal. Why does it stop here? And actually, there is a reason.
The
reason was
only 800.
Yeah, but why?
There's no PUP domains were longer than 800. Its lifespan were longer than 800. But so we can see about it. So given there's a terminals here, so given a malware domains, there's some malwares domains have a long lifespans and some have a short ones, right? Given the short ones, we're asking. So I'm always asking is that what does it mean to be resolved? Resolved because we have domains as I understood. The word resolved means that we can turn such domain into an IP address.
Yep.
It is called resolved.
Yep.
So,
yep.
So in this case, so sometimes the IP address may still alive, but the domain cannot be resolved into an IP address. Is that?
No, that's not the interpretation of this axis.
Okay.
I think it's you can take it simple. The simplest explanation, it's the number of days that it's simply the number of days that this domain was resolved in the data sets,
resolved in the data set, but
because we can.
That is static. The point is that this data set is static.
It's more an indicator of activity. Like if we take 1 point on the diagonal, let me draw.
I got it. So we have a lifespan. It's just showing that giving a lifespan, being resolved is indicator of some kind of capability
of activity. Right? Yes,
it's more like a capability. So giving a lifespan for example, for some people, it have a lifespan of 80 years, and some of them have a lifespan of about 20 years, right? Given the 20 years, and how many, for example, I'm saying that some people may have the capability to study fast. Maybe for some people, they have a long lifespan. They can always keep studying until they die, right? In this case, it's more like at this point. At this point, let's say being resolved is like the being of the capability of studying, right? So if he can live 100 years, if we can live, if the people can live 100 years, and he can always keep studying. But however, if for the people have here, he despite these people can have a lifespan of 100 years, but he can no longer study after 20 years, after he's 20 years, right? So that means that the time of being studied will definitely be shorter than the lifespan. But I'm asking is that resolvable, what's the definition of resolvable or resolvability?
Maybe I should look in the paper to have a precise definition.
Yes, maybe you can just leave the definitions in the WeChat group to see what is the resolvability.
Okay.
Right. So we can make it more clear here.
Yep.
Okay, keep going on.
Maybe I can just say their conclusion then.
Okay.
So their conclusion was that because the density is spread on the diagonal here and not here, it shows that organizations are actually failing to block PUP domains, and that antivirus does not manage to block PUP domains. They are yeah.
Yeah, what? And why it is supposed to be, and why it is supposed to be the antivirus companies cannot block PUP domain?
I don't understand your question.
Yeah, you're saying that the PUP domain, the antivirus company cannot always block the PUP domain. Am I correct?
I said that the researchers interpreted that this diagonal by saying that either organizations fail to block these domains, or antivirus fail to delete the softwares, the PUP.
Okay, so let's have a takeaway, because it's more like an empirical study, right? This paper is more like an empirical study. Let's go.
Yep. Honestly, my takeaway is the things that I found interesting is the way they crossed a lot of data sets to do their analysis, and their filtering process. Maybe we can use a filtering process like to get more.
But for me, I will see this from a very different angle. So giving a malware, suppose it is really, anyway. So this malware will not giving there's such a huge number of the malware, we can never guarantee that all the samples are the real malware. I'm not sure. So assuming that all the samples are the real malwares, I will be very curious, like what legitimate website will this malware use? And
yeah, they didn't mention that. I agree.
Yeah, if I'm the author, so definitely I will not ignore these. For example, a malware can use Google. It's quite reasonable, because for such a legitimate website, it will be using Google to search some things, because Google is most like a tool. And what if the malware is using some PayPal, sending some information to a legitimate PayPal? So what's the plan? What's the plan? And what's its logic? That's all very interesting aspect to look at.
I see.
Yeah. And also, I think there's some confusions or ambiguities in your explanations of the paper.
Yeah, I'm sorry.
Yeah, so,
I think especially for this one.
Yeah, so here we spent maybe 10 minutes to clarify it. Maybe because the skeleton is almost there. So sometimes I rely you and trust you to go through the details. But I'm not saying, but anyway, so there's still has some confusion there. So it's better to clarify it. And that'll be very useful because when you present, the ultimate goal is to let the students get interested in your domains. And then maybe sometimes you can talk about it, not only discuss with me, but I'm always enthusiastic to discuss the academic and research with you. But sometimes if you can have an environment to discuss the technical details yourself, so that will be very so that will be an atmosphere. So it's not for someone to lead a group, and that means the group would have an atmosphere and a culture to moving itself and not driven by me. So that'll be perfect. And also, and for your presentations, maybe you can just fix out this. And now I think let's spend maybe less than 5 minutes to conclude these papers and to see what we can get from this paper.
Okay. So in terms of analysis, the conclusion was that dynamic analysis traces contain a lot of noise and should be filtered according to their method.
But actually, we don't. But for me, I think those noise might be valuable in some sense.
Okay, I see what you mean. They are valuable, but I think it's out of scope of their study. Like what they want to study is the malware malware domains. So I agree that in our research, this noise could be valuable.
Okay, so maybe let me make my last comments on your presentations here. So on your slide, it's saying that a malware's blacklist sometimes may have lifespans, but because Kansin is not here, Kansin is now working on a project looking to the phishing kits. She is going to automatically download a lot of phishing kits given a phishing website. And a phishing website or the phishing kits can be considered as very special kind of malwares. So as long as the phishing case is deployed on a new domain or on an existing compromised website, it will still keep a very short lifetime, just in case it has been discovered and put into blacklist. I think the malware domain blacklist will still have such a need. That's my gut feelings. So giving a malware domain, and people know it is malicious. So some government or some antivirus companies will somehow still block them, right? Block the malware. But
it may take some time.
So as a countermeasure, if I'm the malware authors, I always have a need to, just as you mentioned, to move from one domain to another, or keep updating the domain service to my client malware, right? But what's the difference? What difference from the phishing website is that the phishing website is a visible website, so every user can report it. Every user can report it. But for malware domain, it is almost like invisible, something invisible. So despite the malware have to evolve or change their domain from time to time, but the malware domain lifespan was supposed to be longer than phishing website. For example, the phishing website will have a lifespan of 3 days to a week, but for malware domains, it may last for months or weeks or months. That's just my gut feelings. Okay. So here, Chao has leave. Chen has leave. But I'm gonna say that all what we reported in these weekly meetings are top tier conference paper. For this paper, for Chen Chao's work is published on Usenix, and for Nima's work, where they published, let me check. It's
in SP.
In SP, yeah, SP. So I assume that you will know the effort. Do you know how much effort we need to pay to publish a top tier security conference paper? And Ruofan will definitely know, but Ruofan is not here. Ruofan leaves as well. So it will spend a lot of time to analyze those. But giving your presentation, I feel that this paper can be rejected, giving that feelings. So there must be a large amount of information lost in your presentations.
I try to focus on on what could be useful to our projects.
Okay, so that's great. That's
There is one section I omitted.
Mm.
Uh,
And that's fine. That's fine. So
Yeah.
in this case, I suggest that giving this opportunity, I think, especially for PhD and also I think master students, should take these advantages to clarify and articulate the logics for the papers. Because when you're preparing these slides, it's a very good opportunity to organize your logic or organize your logical chains and prepare what is the best way to present the paper. So that is a very important technique in the future. So when we have a chance to present, I think we can take these opportunities to practice, try our best to simplify the story, to simplify the paper, sharing the story there, and I think that's a good chance to be able to abstract and summarize the story from the paper and make it more intuitive, making it well understood. That will be very helpful.
mm,
So okay, I will
Okay.
have my last comment here. So also thanks Chen Chao, despite he's not here, and also thanks for Nima to present it. They do have something interesting here, but in our next meetings, I expect the students can prepare the slides in a more articulate way, and as long as anyway what you put on the slides, it's better that you can fully grasp it and can well prepared for that for for fully prepared for what it should.
mm,
Okay,
Okay.
let's call it a day. Thanks everyone. And
Thanks a lot.
Junyang to attend. I think Junyang attended this presentation maybe because Junyang hadn't appeared for a long time. He joined the presentations. I think he would like to grab something new and he finds something novel. And hopefully we can have a better presentation to attract the alumni. Okay, let's call it a day then. Thank you everyone. Bye.